In this video, we're going to look at sources of strain and conformational preferences in cyclic compounds. We're going to begin with a molecule called cyclopropane. Many of you, the first time you saw me draw it, say, hey, what's up with that? In an equilateral triangle like this, of course, the bond angles have to be 60 degrees. Okay, so this bond angle here between this carbon, CC bond relative to this CC bond, has to be 60 degrees because that's what's imposed on it by its equilateral triangular shape. Okay, but we know that a tetrahedron wants to be 109.5 degrees. So this inability to achieve the desired bond angles is known as angle strain. Okay, cyclopropane suffers not only from angle strain but also from torsional strain as well. 3 points define a plane. Therefore, these three carbons have to be planar. When they're planar, what you see here is that any adjacent pair of CH bonds are going to be eclipsed. You can't really see it here, but these are eclipsed as well as these over here. If we try to draw a Newman projection, we're going to have to draw an eclipse. It's a little hard to draw it perfectly in the middle here because this bonds would be right on top of each other, but this is an eclipsed conformation. So cyclopropane, we say, is a high energy molecule because it suffers from angle strain and torsional strain. Okay, several years, a chemist named Bayer, the same guy who synthesized aspirin in the 19th century for the very first time, developed a theory about strain. He said that 3 and 4 membered rings would be very strained, and that the strain should go down as you make the ring a little larger. It would be as low as it possibly could be at a 5-membered ring because the angles in a pentagon are 108 degrees, very close to the perfect angles in a tetrahedron, and then start going up as the ring gets larger. So let's look at how Bayer's theory compares with experimental data. And we're going to compare the heats of combustion of all of the cycloalkanes, 8 and smaller, or 8 carbons and smaller. And we can do this because cycloalkanes have the formula CnH2n. So they all have the same empirical formula, if you think about it, CH2n. Okay, so all we have to do is divide the heat of combustion by the number of carbons, and we're going to have a number that we can compare accurately. In this third column over here, I just have the angles in a perfect polygon using this geometrical relationship that the angle is equal to 180 minus 360 over n, where n is whatever the ring size is. Okay, so cyclopropane has the highest heat of combustion per CH2 group of all of the cycloalkanes. Okay, and we see that there's quite a deviation in the desired bond angles from 109.5. Okay, cyclobutane is a little bit closer. The angles in a square are 90 degrees, and we see that the energy per CH2 group is going down. Cyclopentane, it's 658. It's down a little bit further here. It's very close to what the perfect bond angle is in a tetrahedron. But here's where Bayer's strain theory starts to fall apart a little bit. Cyclohexane is actually less strained than is cyclopentane, even though its bond angles in a perfect hexagon are deviate a little bit more from 109.5 degrees than the perfect pentagon. And it starts going back up when we go from 6 to 7, but it doesn't go up quite as dramatically as you would expect based on these angles here. We're deviating more and more from the perfect bond angles of a tetrahedron. Okay, so what's wrong with Bayer's theory? Okay, let's see. Bayer's hypothesis is a little bit off because rings are not flat. Flat rings suffer from torsional strain, and thus rings don't want to be flat. Rings pucker to avoid torsional strain. Puckering decreases the bond angles a little, but relieves the torsional strain. Predicting the conformations for 4 and 5 membered rings and for 7 and larger membered ring is somewhat difficult. We'll see that 6 is the real champion. Before we do that, let's do a problem here. Sorry that it's out of order, but let's just rank the following compounds with regard to their anticipated heat of combustion. And we can do this without doing any division because all of these have the same formula. These are all, I guess C9H16 would be the formula for all of these. We're going to rank the one with the highest heat of combustion as number 1, and the one with the lowest heat of combustion is number 4, and fill in numbers 2 and 3 where appropriate. Okay, and again, you should pause the video and do this, and then just come back and see how your answers compare. Alright, so the issue here is we're looking for strained rings. 3-membered rings are the most strained of all. Okay, and some other things we may notice is that the 6-membered ring is the most stable ring system, and it's starting to go up as you go from 7 to 8. Okay, so if we look at these ring systems, okay, there's our ranking as far as the ring strain goes. So we're going to predict that the ones that are going to have the highest heat of combustion are going to be the ones that contain a cyclopropane ring, i.e. this one or this one. Okay? And the other ones will be less strained. Okay, so how do we do this? Well, this has got a 3 and an 8. This one has a 3 and a 6. Okay, so we see that an 8-membered ring is more strained than a 6-membered ring. So we're going to predict that this one on the far left is going to have the highest heat of combustion, and the next highest is going to be the one on the far right. If we compare the other two, this one here doesn't have any no rings with high angle strain here. Whereas this one does have a 4-membered ring, or a cyclobutane, right? And remember, those have a high degree of angle strain, not as much as a cyclopropane, but they do have some angle strain. Okay, so our predicted ranking is that the one on the far left has the highest heat of combustion, followed by the one on the far right, followed by the one with a 4-membered ring, and the one with the lowest heat of combustion, or the most stable, is this third one in that has a 6-membered ring and a 5-membered ring. Okay, so let's look at conformational preferences. Cyclohexane is widely considered to be almost the perfect molecule. We can write a conformation of cyclopentane that's essentially unstrained. Okay? And that conformation is called the chair. The chair is the most stable form of cyclohexane. Just look at it here with the hydrogen atoms drawn. Every carbon-carbon CCC bond angle is 111 degrees. That's very close to 109.5. And most importantly, perhaps, we don't have any adjacent carbons that are eclipsed. They're all perfectly staggered. Here on the right column are some other conformations of cyclohexane. Flat, of course, is the least stable. This is because we're suffering from angle strain and torsional strain. It's getting closer as we do more and more puckering. Here in the boat we have the right bond angles, but we have a pair of carbons eclipsed there and a pair of carbons eclipsed there, so we haven't fully removed all of the eclipsing interactions. A twist boat is another conformation that is starting to relieve most of the strain, but not quite. The chair is the only one that totally relieves the torsional strain. Oh, look where I got this from. Okay, sorry. All right, so we're thinking about conformational preferences in cyclohexanes. Chair is really going to be 95% of the game, okay? It's by far the most important of the conformations. Okay, so why do we call it a chair? All right, so there's Homer taking it easy on his lazy boy cyclohexane chair. If you're looking at cyclohexane, you may say, have I seen that before? Yeah, probably at the bar. Budweiser uses chair cyclohexane as their official logo. All right. In this last column here, all my cyclohexanes are pre-drawn, but you really need to just be able to draw a cyclohexane, so let's do that. Okay. And I'll get into the importance of artwork a little bit later in this video. Okay. If we look at the hydrogens in cyclohexane, there are 12 of them. Okay? But there's something different about we can divide them into two classes. The ones that are in magenta go either straight up or straight down. And we're going to give these the term axial hydrogens. Okay? The blue hydrogens are going off to the side, and we're going to call these equatorial hydrogens, axial or AX. Okay, I've numbered this arbitrarily. I've just taken that as carbon 1. According to IUPAC rules, any one of these could have been carbon 1. They're all identical carbons, but I just put that one as carbon 1. Notice that the axial hydrogen is down at carbons 1, 3, and 5, and it's up at carbons 2, 4, and 6. This alternating relationship is an important feature of chair cyclohexane. Notice that it's very obvious which axial hydrogens are pointing up and which axial hydrogens are pointing down. But it's not so obvious for the equatorial hydrogens. For example, this one, there's a slight net upward trajectory here, but it's not an extreme upward trajectory like it is for this one here that's definitely on the bottom side of the molecule. So it's a little hard to tell which face of the molecule an equatorial hydrogen is on compared to an axial hydrogen. Okay, at room temperature and temperatures well below room temperature, cyclohexane is undergoing a conformational inversion known as a ring flip. In a ring flip, what we're doing is we're sort of taking carbon 1 and moving it up, and we're taking carbon 4 and moving it down. We're doing a simultaneous rotation around this CC bond and around this CC bond. Okay, look at what the ring flip does. It totally interconverted what was axial and what was equatorial. So look at C1. The blue hydrogen is now up and axial. The magenta hydrogen is now down and equatorial. Okay, so let's just compare those two. C1 and C1. Okay, so this is a feature of the ring flip. It totally interconverts the axial and equatorial relationship at every carbon of the cyclohexane ring system. Okay, and you see that this has happened at every other carbon in this molecule as well. Okay, let's add a methyl group here. Here, if you have to ask what is the equilibrium constant for these two compounds, it's of course 1. They're really identical. Just because I've colored some hydrogens blue and some another color doesn't make them different. Okay, but when we go to methyl cyclohexane, the equilibrium is no longer 1 to 1. Okay? At 25 degrees C, methyl cyclohexane prefers the compound that has an equatorial methyl group over the compound that has an axial methyl group by about a 19 to 1 ratio. Delta H, sorry I didn't Greek that D there, delta H for this process is plus 7.3 kilojoules per mole or plus 1.8 kilojoules per mole, kilocalories per mole. This number in kilocalories, by the way, is a quantity known as the A value. We'll look at that in a future slide, but this is a measure of how sterically large something is. Okay, much larger than a methyl group is a tertiary butyl group, and here we see an incredibly higher preference for equatorial. There's essentially no axial T-butyl compound present at equilibrium. The ethyl is just a little bit larger than a methyl, and here we go from 95% equatorial to 97% equatorial. Okay, what's the reason for the destabilization of methyl in the axial position? Okay, if you look at this drawing here, here's the methyl and we're putting it at C1. If we look at C3, which is right here, and C5, which is right here, we have an axial hydrogen sticking up. Okay, and this is bumping in to the electron cloud of the methyl group. Okay, so there's the methyl group's electron cloud here. There's this hydrogen's, that's this hydrogen's. So there's a steric interaction right here. We call this type of interaction a 1,3 diaxial interaction. It's really like a gauche interaction, except it's a little bit more severe because this axial hydrogen is stuck in the worst place it can be. Here it is over to the right, drawn as a double Newman projection, and here you can see how the methyl group is engaged in diaxial interactions with the hydrogens at C3 and C5. Okay, we're citing C1, C2, and C4, C5 simultaneously in this Newman projection. Okay. Here's a table of A values. Here's our methyl group right here. Okay, this trend here that ethyl is larger than methyl, isopropyl is larger than ethyl, and T-butyl is larger than all of them is totally expected, right? Because here we're taking the hydrogens of a methyl group and replacing them with alkyl groups, and that's exactly what we expect. Okay, if X groups here, or Z groups here, don't have any hydrogens on them, they tend to have relatively small A values or small preferences for equatorial. So the preference of fluorine for the equatorial position is not very high. Chlorine's a little bit bigger. Bromine, I guess there's some disagreement as to what its A value is, and iodine's a little larger. These atoms have longer bonds, so the fact that they're larger atoms is counterbalanced by the fact that they're being pulled further away. Okay? And we see that also, actually we don't really see it with SME versus OME. Okay, so here with the oxygens we have a substituent, and they have all slightly larger A values. Here nitrogens have two hydrogens, and they have larger A values typically than the oxygens do. Phenol's fairly large. Here we see that we have some sp2 carbons, so that we don't have quite as many hydrogens, so a carboxylic acid group like this is actually smaller than a methyl group. The cyanide has no hydrogens right at this carbon, and its A value is also quite small. Okay. All right. So let's move now to systems that have two groups in the ring. And this is going to take us to a new type of isomers. These are called diastereoisomers or diastereomers. They're only isomeric in the third dimension. Okay? So let's take 1,2-dimethyl cyclopropane. We can put the methyls on the opposite side. This is called the trans isomer. We can put the methyls on the same side, and this is called the cis isomer. If we want to think about how would these two interconvert, the only way you can do this is to break that bond, rotate this sucker around, then reform the bond. And that's an energetically rather costly process. It's not going to happen. So these are two distinct compounds. You can isolate them and separate them. They have different physical properties. They're different in their boiling points and a lot of their spectral properties. Okay, these are stereoisomers. We're going to see several types of stereoisomers when we go to chapter 7. They're only different in the third dimension. This is a type, again, where we're going to call it diastereomers or diastereoisomers. This means that they're different at least two of the stereo centers right here. Okay, we'll take a look at diastereomers in chapter 7. You'll appreciate what they are when you see other types of stereoisomers in that chapter. Okay, the greater stability of trans. Notice how trans has a lower heat of combustion than cis does. It's 3371 for the cis isomer, 3366 for the trans isomer. The trans isomer is more stable by 5 kilojoules per mole. Okay, so what we have here is a steric interaction between the two methyl groups. Okay, they're a little bit close here. They're eclipsed. They're kind of like eclipsing butane, but not as bad because the bond angles in cyclopropane kind of take them a little bit further apart. Okay, but this steric destabilization accounts for why the trans is more stable than the cis. Okay, let's look at stereoisomerism and cyclohexanes. This is a very interesting case here. All right, so if we look at cis and trans cyclohexane, the cis isomer is also less stable. It might be tempting to just say this is like cyclopropane, but that's not the case because cyclohexane's not a flat molecule. Cyclohexane's a chair, so we have to think about the chair when we're thinking about why is the cis isomer less stable than the trans isomer. Okay, so if you want to really analyze this question, what you have to do is you have to draw it in the chair conformation and then ring flip it to look at both ring flip stereoisomers. Okay, so here we have cyclohexane and it's cis. Okay, we have to have cis means both methyls have to be on the same face of the ring. Okay, it doesn't mean necessarily axial versus equatorial. All right, so how do we know they're on the same face? Okay, you just look at the axial thing and say that axial thing is up, this axial thing is down, and wherever the axial is, the equatorial at the same carbon is in the opposite orientation. Okay, so this is up, and this hydrogen here has to be down. So the fact that it's two ups means that we have the cis isomer. Now we're going to ring flip it, put that end down and this end up, and what you see here is that, of course, we interconvert the axial and equatorial at every position. So at C1 we have an axial methyl, and C2 we have an equatorial methyl. Okay, all right. So no matter what we do, we have two ring flip isomers, and both of them show that there's going to be one axial methyl group and one equatorial methyl group. Now let's do a similar analysis on the trans. Okay, sorry. Let's correct this. All right, so carbon 1 is up, carbon 2 is down, sorry. Okay, if we look at this, all right, so the axial, that one's definitely down. That one's definitely down, up. That means this has to be down. And this has to be down. Up, sorry. Up. Okay, so we have up methyl and down methyl. That means they're trans. Notice that both methyls are equatorial. We can ring flip it, but we really don't want to ring flip it here because this puts both methyls axial now. But this is also a form of the trans isomer. Okay, so this one's the equilibrium is definitely going to go to the left because the methyls want to be equatorial, just like they did when we had one methyl group. This equilibrium constant here, by the way, is perfectly one-to-one equilibrium. Okay, so the reason that trans is more stable than cis is because there is a conformation where every methyl group can be equatorial. In the cis isomer, when you draw the chair form, at least one of the methyl groups has to be axial. So that's destabilizing, and that's why the equilibrium is favoring, or that's why the trans isomer is more stable than the cis. Okay, I'm going to leave this one to you as a problem to figure out what are the relative energetics of 1,3 and 1,4 dimethyl cyclohexane. So in this problem, again, you should pause the video and do this, but what we're going to do is assign cis and trans to each species. The top set is the 1,3 dimethyl, and the bottom set is the 1,4 dimethyl. Okay, and for each of these we're going to predict which of these is more stable. Okay, we're going to assign cis and trans and predict which is more stable. All right, let's do that. Methyl is up. There's a hydrogen there. This hydrogen's up, therefore this methyl is down. One methyl up, one methyl down. This is trans. Okay, both of these are equatorial. They're a little hard to see. You can see the methyl is in a net downward trajectory, but let's just draw the axial hydrogen so we can be sure. This is up, up. Therefore, this is down, down. Okay. This is the cis isomer. Okay. If we look at this one, 1,4. Again, this is has two methyls equatorial. That's up, down, down, and up. Methyl up, methyl down. This is trans. And again, up for axial hydrogen, down for methyl, obviously down for the axial. Okay, so this is down, and this is cis. Okay, so notice some interesting things about this relationship. 1,3, cis is diequatorial. 1,4, trans is diequatorial. 1,2, trans is diequatorial. Okay, so 1,2 and 1,4 have the same orientations in the cis and trans isomer with regard to what's axial and what's equatorial. But 1,3 is opposite to both 1,2 and 1,4. This gets to this relationship we're looking at when we look at just cyclohexane all by itself, that we have the opposite relationship at carbons 1, 3, and 5 as to what's axial versus equatorial or up and down versus carbons 2, 4, and 6. Okay, so it's important to separate the concepts of cis and trans from the concepts of axial and equatorial. They are related, but in kind of a strange kind of way. Okay, it all depends on which two carbons they're on. Are they both even carbons, or both odd carbons, or one even and one odd? And that matters greatly, but that's kind of confusing. So you want to consider whether it's up and down first to decide whether it's cis or trans, and then decide whether those substituents should be axial or equatorial. Cis and trans, axial and equatorial, are not necessarily the same thing. Okay, here's the answers in just a separate slide. It just goes through what we had in the previous slide in a much neater fashion. Okay, I want to get to a point of artwork. Avoid bad art. I want to just say carbon is tetrahedral. And when you draw cyclohexanes, you should draw it in such a way that carbon looks like it's tetrahedral. Look at these asterisk carbons here. They don't look very equatorial, do they? Okay? And one of the problems here is that when you're looking at a cyclohexane, you want to look at where it is and say, is the vortex down on the downside of this 3-atom plane, or is on the upside of this 3-atom plane? If it's on the downside, then axial has to be down. Okay? And if it's on the upside, axial has to be up. So these are all down. And that's how we have to arrange our substituents. These are all up, and axial needs to be up. Okay, another thing I'd like to point out, let me just give you another example of a bad drawing. Okay, so there's axial correctly in the up position. Okay, your equatorial, there should be a net downward trajectory here. Okay, so we this is not really right here because the equatorial group is just going perfectly straight off to the side. There's no net downward trajectory to it. Okay? So axial is definitely up, equatorial's down. There needs to be a net downward trajectory to the equatorial if axial is up. That's a Q, equatorial. All right, this is a question that I put on the exam. It might seem like a little simple for a college level organic chemistry exam, but this is what I'm looking for in a question like this. Draw a pretty picture of chlorocyclohexane where the chlorine group is axial. Okay. This isn't necessarily going to be all that pretty because I am drawing it on a pad instead of a piece of paper. Let me draw it again. Okay, so you need to, this is just generally sucking. I think it's because my pad is at an angle. I look at it here. Yeah, that's the problem. There we go. All right, so I'm going to get a lot of credit for that. All right, so on this question here, I was kind of what you call a severe art critic, maybe like one of those people that work for the New York Times or something. I was looking to just make sure that you can draw a good chair picture with the hydrogens and chlorines in the correct axial and equatorial arrangement. So we're supposed to draw in the hydrogens on the adjacent carbon as well. And I was looking to make sure that these equatorial things were, that when the chlorine was axial, the hydrogen at the same carbon had a net downward trajectory, and the adjacent one, the equatorial hydrogen, had a net upward trajectory. Okay, so get in the habit of drawing cyclohexanes as perfectly as you possibly can. All right, we're going to end this one with another problem. Draw the most stable conformation possible for cis-4 ethyl 1-chloro cyclohexane, and note that the ethyl's bigger than chlorine. That's going to be your guiding principle. Again, pause the video and do it yourself, but let's just go. I'll go ahead and present the answer, but you should have done it. Should restart the video after you do the problem. Okay. All right, so when it's 1,4, we have to have both up or both down. Okay, so here I put ethyl axial and up. Chlorine thus has to be up, and if it's at carbon 4, the cis will have one axial and one of them equatorial. All right, our ring flip isomer just puts ethyl equatorial and chlorine axial. All right, so we're going, we would predict that the equilibrium would go to the right since ethyl's bigger. Ethyl has the greater preference for the axial spot, okay? And so this equilibrium should go to the correct, go to the right. All right, some of you are probably saying, I can draw an even better conformation than that one, where everything's equatorial. But that's not right. You know why? Because whoever wrote this question said that it had to be the cis isomer. This is trans. Okay, so you have to stick to the problem. And whatever you give has to be a representation of the cis isomer. You can't have a representation of the trans isomer. Okay. All right, so this is where I'll stop this video, and we'll resume part 3 for the rest of the conformational analysis chapter.